So what we're going to look at is trends in electron affinities. We've seen in first year chemistry trends in ionization energies, but we wanted to see some trends in electron affinities also, because that's what's tested in second year stuff also. Now, earlier we had seen one basic idea. We saw first and multiple electron affinities, and we've discussed that already. If I were to ask you to write the equation of the first electron affinity of chlorine, you would have written that to be Cl gaining 1 mole of electron to become Cl minus. But we know with oxygen becomes a 2 minus ion, so it needs first electron affinity and then it gains a second electron to become O2 minus. The first one is called the first electron affinity of oxygen, first electron affinity of oxygen. It can also be called the electron affinity of O. The second is called either the second electron affinity of oxygen. It can also be called the electron affinity of O minus. Sorry, the first one is yeah. And what we've discovered is that the first electron affinity is generally exothermic, but the second one is always endo. We've discussed this earlier. So this second is always endo. And having discussed forces inside the atom, we know why this is endo, because this guy is already negatively charged particle and you're putting in a negative particle. So the second electron affinity of oxygen is an endothermic value, while the first is oxygen is exothermic, because as the second electron approaches this negatively charged ion, there is repulsion between the electron and the other electrons already inside the ion, and also the ion having a negative charge. So there's more repulsion here, which then requires you to put in energy to insert this negative guy inside the atom. Hence, work must be done to force this electron inside the ion. So we're kind of forcing this guy in. Hence, the second electron affinity is always endo. Now, this is the stuff that we've already kind of done. What we're going to talk about is understand how electron affinities vary and what forces affect the variation of electron affinities. Now, if I looked at any of this stuff, like visibly, when I talk about any electron affinity, let's say chlorine, what I'm saying is that we are talking about how chlorine atom, for example, these are chlorine is 2 and 8 in the second one, and then let me just and 7 in the third one. These are the electrons in chlorine. You got 2 electrons here, you got 4 6 and 8 in the second shell, and then 2 4. This is how we've been drawing it in earlier years. An electron affinity for chlorine is when the nucleus of chlorine pulls an outside electron into its atom. So it's being pulled by the internal electron and it takes up space right here. So the force the outside electron or the outside electron feels, this force is similar to what? Similar to the force the outer electron feels. Remember that. The physics is the same. It's the same force. It's the force from the nuclear charge. And if you remember, what affects this force that the outside electron feels? If you remember, there were 3 factors that affect this force. So this force of attraction, the factors, its factors are what? Now we've seen these factors already in AS level. One is nuclear charge. Okay. And the greater the nuclear charge, the more the force of attraction. The second is the distance between electron and nucleus. And we saw that as the electron is further away, it's attracted less. And the third is repulsion between the inner shell electrons and the outer electron that we refer to by the term shielding effect. So 3 of these factors, and these are, by the way, the same factors that affected ionization energy and even atomic radii. For those of you who've done this with me in first year, we just, it's the same exact idea. Now, so technically speaking, electron affinity measures the attractive force between the incoming electron which is the outside electron, let's call it incoming electron, and the nucleus. And the stronger this force, the more exothermic the first value is, the first electron affinity. Now we are discussing the trends as only the first electron affinity, nothing else. So I'm talking about when the neutral atom gains the first electron. So this force is, obviously if the force is stronger, it'll be easier to pull the electron in, therefore more exothermic. So electron affinity is also a measure of the attractive force the nucleus has for the incoming electron. And obviously if the attraction decreases, it'll become less exothermic, and if the attraction increases, it becomes more exothermic. Yeah. Now all of these three factors do increase or decrease the attraction. So now obviously if nuclear charge increases, we know that the force of attraction will increase. Therefore, if that is the only factor changing, electron affinity will become more exothermic.
Quick pause. If you're finding value in this explanation, there's so much more to discover at Alt Academy, where we break down every A-level concept with the same clarity. Now back to the video lesson.
But at the distance, because remember the idea is that the greater the force, so you can say greater force of attraction results in what? More the first electron affinity. That's the game. So, and I know that as nuclear charge increases, there's greater attraction. So nuclear charge increasing should result in more exothermic ionization energies. Okay. But as you go down the group, or as you go, if you go down any periodic group, you know that down the group the number of shells increase. And when you increase shells, they do two things. So these two, as shells increase, 2 and 3 will increase. So as you go down any group, what you know that shells increase. What that means is the distance of the incoming electron from the nucleus will increase, and also the shielding effect that prevents, or that is the repulsion between inner electrons and the outer electron, also increases. And we had done this in AS, that down the group these two factors which decrease the force of attraction outweigh the factor that increases the force of attraction. But along a period, what happens along a period, nuclear charge increases, but the shielding effect stays the same and the distance decreases. So what we've discovered is that, because if you remember in a periodic table, and I'll make a small little box right here, okay, in a periodic table, as you were to go from left to right, nuclear charge increase, therefore force of attraction increases, because across a period nuclear charge would increase, shielding would remain the same, and the atoms would get smaller, so the force of attraction increases. And therefore in AS we had done this, that ionization energy increases. And down a group the force of attraction decreases. Remember that. So across a period, force of attraction increases for the outer electrons, down the group it decreases, which means in AS ionization energies increase because the force of attraction increases, and ionization energies are endothermic, so they'll become more endothermic. Atomic radius decreases because the attraction is more. And now we are learning that across a period, first electron affinity would also increase, will become more exo. And down a group, first electron affinity will become less exo, because down a group, even though nuclear charge increases, the distance between the electron and the nucleus increases and shielding effect increases. Both decrease the force of attraction. So that's why the physics of the atom is so important. The understanding what the variation is between nuclei and outer electrons, but be it them on the outermost shell or incoming. If that force of attraction increases, that is because nuclear charge increases. But if it decreases, it's because the shielding and the distance and have outweighed the increase in nuclear charge. And as the force of attraction increases across a period, it's harder. Think about it. As you go across, it's harder to lose the electron as being more ionization energy, but easier to gain. Down a group, harder to gain, easier to lose. So that's why electron affinity is gaining and ionization energy is losing. So one easiest thing is across a period, easier to gain, harder to lose. Down a group, harder to gain, easier to lose. Because as you get bigger, it's harder to lose. Sorry, as you get bigger, it's easier to lose, harder to gain. As you get smaller, it's becomes harder to lose, easier to gain. That's what you gotta remember. All right. Now let me show you this in terms of actual numbers. So in a periodic table, I'll draw that again. I'll take, okay, let me just make a larger one if I can. Come on. Okay. So this is a big box now. And let's say we've got oxygen here and fluorine here and chlorine here and bromine here. Now, what we've discovered is the first electron affinity for oxygen is, if you notice, I'll just write it down here. First EA of oxygen is about minus 142. Let me get the value. Yeah, minus 142. And the first electron affinity of the guy after it, fluorine, is minus 300 and something. I have the value here also. I had them saved beforehand. Minus 333. So this is just, I am talking about first electron affinities only. So for oxygen, it's minus 142, and for fluorine is minus 333. And to make sure that I'm talking about these guys, I'll make it even closer. Okay. And as we, what do we see? Across a period is becoming more exo because it's easier to gain. It's easier to gain because your nuclear charge is increasing. So here, across a period, nuclear charge is increasing, which means that its attraction is increasing, therefore it's easier to attract, therefore more energy given out when the electrons are attracted. But as you go down the group, we've discussed this, that the first electron affinity will decrease, will become less exo. And why will become less exo? Because shielding effect, also known as screening effect, shielding effect and size or distance outweighs what? Just like it did for ionization energy, outweighs the increase in nuclear charge. That's what's happening. Now let me give you the actual values for these guys. So the value for group 7 down the group, and you don't have to learn these values, is that there is an anomaly for fluorine and we ignore that. But generally speaking, the values start decreasing. So this becomes 348, bromine is 340, and the guy below that is iodine, 340, and iodine is about minus 297. Now there's a reason why fluorine has an anomaly. It's really small, so that's why we don't even study fluorine in group 17 properties, because that is an anomaly. An anomaly is something there are other reasons to explain it. Anomaly. But what's really happening is, if you notice the values are decreasing, becoming less exothermic. So those are what you want to remember. So from chlorine to iodine, what's happening is the attraction of the nucleus for the incoming electron gets weaker, because the increased distance and shielding effect outweigh the increase in nuclear charge. Okay. Now fluorine is an anomaly because it's very, very small, and when it becomes very, very small, it's hard to predict. It doesn't always follow the exact predictions perfectly. Okay, so we tend to ignore that, but everything else is the same. Yeah. Now another thing, if you think this, okay, let me tell you sulfur. Now sulfur is just before oxygen, and sulfur's electron affinity is supposed to be lower than oxygen's, but because the period 2 is smaller, we have that problem. We have some anomaly. So that's why in AS also, when we study, we don't study period 2, we study period 3. Okay, less exothermic means a little more difficult to gain the electron or less easier to gain the electron. More exothermic means more easier to gain the electrons. And so you should appreciate that across a period, electron affinities will become more exothermic, easier to gain, and down a group they'll become less exothermic, less easier to gain. And that's the trend in first electron affinities. Now, when they want you to compare, they won't ask you to compare things which are not in the same period or in the same group. So for example, they can ask you, well, I can either compare sulfur with chlorine or chlorine with bromine. I will not be able to compare sulfur with bromine here. So similarly, if I were to ask you the relationship between the first electron affinity of sulfur versus the first electron affinity of chlorine, whose is more exothermic? Okay, so across a period it becomes more exothermic, so chlorine's is more exothermic or greater in magnitude. And they can kind of ask that also, right? And you can say, okay, well, how about you predict that for nitrogen versus oxygen, or you know, I just forgot what comes below this, but yeah, that's it. Yeah, so between these two, oxygen's is more exothermic, and that's really the predictions I'll be looking for in terms of this. And that just wraps up the trends in electron affinities. Hey there, if you found this A-level chemistry lesson helpful, why don't you head over to our website altacademy.org, where you can sign up for the full A-level chemistry course. In addition to chemistry, you can sign up for physics, biology, math, or 4 other A-level subjects. Thousands of students have already taken the leap. What are you waiting for?